Okay, I'll show this slide again so it appears in the video. And as I said, they're interesting for practical reasons. They're always in operating system. So when an event comes, or a data packet or something, and it cannot be processed immediately, it's going to be saved. And then the next one comes, it's going to be saved after it. And then the next one comes, it's going to be saved after it. Now, when you're ready to process it, you take the first one. And then you take the second one. But now, in the meanwhile, another one might come, and you queue it up. And you can see how things are added from one end, and they are removed from the other end. And the queue can also become empty, and then the whole thing just kind of carries on like this. So we add, a queue is a data structure where we add to one end, and then we want to remove from the other end. It has a notion of front and back. So the way we construct the queue is different from the way we destruct the queue. In the case of the list, we had the symbol that had two columns, and that served both as a constructor to create a longer list by adding a new head, but also served as a destructor that you could use in pattern matching. So when you pattern match on the list, you can use the column so that you separate the head from the tail. And that is very convenient when the constructor matches the destructor, because you can write inductive definition, and you can prove things by structural recursion. But in the case of a queue, that's no longer the case. The destructor and the constructor no longer match. And because of that, we don't have any native, let's say, principle of recursion. We don't have any native principle of induction. So it's a data structure unlike the ones that we have seen so far. The ones that we have seen so far, the lists, the things that we can do with lists, like numbers, and the trees, are all inductive. So when you define a tree, it doesn't matter what the exact shape it is. Any shape it has, if it's a tree, it has an associated inductive definition and an associated recursion definition for functions. So this is something that is new about queues. And in fact, a lot of the data structures that you see in programming, especially in operating systems, are going to not be inductive data structures. And that's because they are designed to model arbitrary situations that happen in real life. And in this case, they model a situation that happens especially in operating systems, this need to process events as they come. So how do we implement it? Well, you have seen the behavior, and we can have a naive implementation. We can kind of have a very straightforward implementation where we say a queue is just a list. Yeah? So it's just a list of events, and we make an arbitrary decision which end is the front end and which end is the which end is the back end. Yeah? A list has a front, but that's not necessarily how you implement it. So let's define now in terms of a list. So a list, the operations that would give us a queue. So the first basic operation is adding to a queue, or enqueuing. So if we want to enqueue element X to a queue called Q, then just like in the case of a queue at the checkout, we just put it at the end. And how do we put it at the end? Well, we cannot use a special constructor, but we use the append operator. So we make a one-element list called X between square brackets. So we make a list out of one element. And using append, we put it at the end. Okay? And we can have a dequeuing operation, which is just taking the tail of the list. So we discard the front element and we take the tail. Okay, so it's a very simple implementation, and also these are the main operations that that serve as the constructor enqueuing and the destructor dequeuing of our data structure of our queue. But then we might have other functions for convenience. We can have an empty function that tests whether the queue is empty, because of course if the queue is empty you cannot dequeue, you will get an error. And also we can add things such as peek, so that we can see what is the element at the front of the queue before we discard it. Now, of course, you can write variations on this. You can write the dequeue operation that both removes and gives you the first element, and so on. So this is not intended to be canonical. This is just intended to be simple. But taken together, these collections of functions gives you the interface to the data structure. So once we set an interface in place, and that's something that I'm sure you have learned in object-oriented programming as well. Once we set the interface, in our case these 4 functions, then we try to forget how it's implemented. The queue, we just think of it as a collection of operations: enqueuing, dequeuing, empty testing, and getting the front value. Okay? So how do these naive queues behave? Well, they behave a little bit differently than the ones that I showed you in the initial animation, and I'm trying to make a slightly more accurate animation. So when the first element comes, is the same, but when the second element comes, remember how the append operation works. It has to it cannot append directly at the end of the list. It has to take smaller and smaller lists, and only when it reaches the empty list, it can actually append the list that you want to append. So every new element that comes into a queue has to go past all the elements that are already in the queue in order to find its place at the end of the queue, and so on. Now, when we remove, that's very easy. It just comes straight from the top of the queue. So we just apply the tail function, and if you remember how the tail function works, it just pattern matches the list against the head and the tail, and then it forgets the head. So removing from the queue, it's only going to take one operation. But adding to the queue is going to take as many operations, as many elements you have in the queue. So that is a bit unfortunate, because obviously we would like both adding and removing to be very efficient. In this case, we have removing very efficient, it happens in constant time, but adding happens in a time that's proportional to the size of the list. So enqueuing takes size operations, where size is the size of the queue, but dequeuing takes only one operation. And that is just not good enough. Having a constructor working in a time that's proportional to the size of the data structure is just not good enough. So there are many other solutions other than this naive solution. Some solutions, which are the most efficient, cannot be implemented in functional programming languages. You need programming languages which, well, actually they can be implemented in functional programming languages like OCaml, but not in the fragment that we have seen so far. OCaml also has objects, also has assignment, and has the standard imperative features, but I think it was complicated enough with what we had. There was no need to to throw imperative features into the mix as well. So if we want to really implement them efficiently, then we have to use imperative features. But we can still do a good job with, good enough job just with functional programming without assignment. And the solution is called the banker's queues. I'm not sure why they call the banker's queues, but it seems to be very simple-minded, and it seems to be very inefficient. But we'll look a bit at it in a bit more detail and see that that's not actually the case. It is quite efficient. So the banker's queue is, instead of having one list of elements, you have two lists. One that represents the back of the queue, and one that represents the front of the queue. So the whole queue is the append of the front and the reversed back. So how do they work? Well, when we add to the back queue. So when we add to the back queue. So we always add at the head of the back queue. And because we have an efficient constructor for the head, that only takes one operation. So we just keep happily adding to the back queue. And at some point, we are going to need to dequeue. And the dequeuing always has to happen from the front of the queue. But in this case, the front of the queue is empty. So whenever the front of the queue is empty, and you want to make a dequeue, you just take the back queue, you reverse it, and you put it at the front queue. So the first dequeuing that you need to make is going to have a fairly big overhead. But once we've done that, whenever we need to dequeue, now it's very efficient again. We just dequeue from the front of the front queue. And adding to the back queue is still efficient because we just keep adding, also using the constructor. So how does this banker's queue work? Well, now when we add to the queue, is only one operation because we add to the back queue, and we just use the constructor of the list. When we remove from the queue, it's also efficient. It's also just one operation because we remove from the front of the front queue, which is just applying the constructor, well, the destructor of the list, which is the same as the constructor. But once in a while, we have a spike in the overhead. Whenever the front is empty and we want to remove from the front, then, well, we cannot do it as efficiently as usually by doing it in one step, but we have to shift all the back queue, reverse it, and shift it to the front queue. Okay? So this doesn't seem to be much more efficient, but it actually is a lot more efficient. So let's look into the implementation of the banker's queue. Okay? So this time, the queue is going to be a pair of lists. F is the front and B is the back. And enqueuing element X means adding it to the back queue. And I put it in blue, and you can see that it's just one operation. It's just the adding of constructing a slightly longer list using X as the head. Now, dequeuing from the queue represented by the front and the back list, now we have to look at, we want to dequeue from the front, but we can only do that if it is empty. So what we need to do is to test if it's empty or not empty. And depending on whether it's empty or not empty, then we can do two different things. The easy bit is if it is not empty. That if it's not empty, then we can pattern match on the colon operator, which is the constructor of the list, and find the head and the tail. and we simply drop the head. So it's just one operation, and then we're done. Something that's more complicated is the case where the list is empty. So first we have to reverse the list, the back list, and then we have to move it in front after we remove its head. So we have to do several things. First, we have to make sure that F is empty. Then, if it's empty, we have to reverse B. And after we reverse B, we have to remove its head. And then we take the tail and we put it instead of F. And that's just, in OCaml, we just write it in one line. So we call, the way this is going to be executed, first we call reverse on B, and that's going to give us the reverse list of B. And then we're pattern matching again X, colon, XS, to see if it's, to take away its head. And we drop the head, X, colon, and then we put XS instead of F. And we leave the back queue empty. And when you put this code in the OCaml interpreter or in the OCaml compiler, what's going to happen? What's going to happen? You are going to get a warning. Why? Anybody else? Why are we going to get a warning?
Because they're not allowed to take into account rev B is empty.
Yes. So we're not taking into account rev B is empty, and that's just for sake of simplicity. If you wanted to write a nice library function for dealing with for dealing with queues, then it would be nice to have another explicit case there where it says if B is empty, then I throw an exception. You have learned about exceptions by now. You throw an error or an exception and you say it's an illegal operation. Right now what's going to happen at runtime with this implementation, if you keep it like this, at runtime if you try to dequeue from the empty queue, do you know what error you're going to get? You're going to get something fairly obscure, something like pattern missing. And it's going to make it even harder to debug than the usual OCaml programs. Whereas if you throw a deliberate error, when you say, I'm failing because the list is empty, then the user can be more informed about what is going on. Thank you. And finally, we have our empty tester. The case is empty because when both F and B are empty. I didn't write the peek function because it would be more complicated. So in words, how would you write the peek function here? If you just look at the top, if you want to see the top element, how would you write the peek function? If you want to see what's the first element in the queue. How would you write it? Yeah. So dealing nicely with peek would require a bit of a more complicated implementation. And also it would be unpleasant because peek itself now would have, sometimes it would work in one go, sometimes it would work in, it would take a long time to get to the head of the other list and tell you what that element is. Okay, so I didn't put it here, but it could be put in here. So now let's see how do these two implementations compare. So just do a very simple performance comparison. Q is the naive implementation, BQ is the banker's queue implementation. So let's say we start with an NQ operation. In both cases, it's going to take one operation, one in each cases. If we add another element into the queue. If we enqueue again, in the naive implementation, now we're going to have 2 steps because it's appending at the list of that has 1 element. In the case of BQ, it's just going to be 1 step because it's appending using the constructor. And now you can see that with every new enqueuing, the number of operations in the naive implementation is increasing by 1, whereas in the case of the binary of the banker's queue, it stays 1. Now, where the naive implementation has the edge is when you want to do the first dequeuing. When you want to do the first dequeuing, the naive implementation would let you do it in 1 step, whereas the banker's queue first will take 4 steps to reverse the front queue and then produce the result. And now if we keep dequeuing, well, if we keep dequeuing now, both of them are going to take 1 step. So if we keep dequeuing 1 step, and now the queue is empty. So I have added a bunch of elements and then I have removed them. So if we just total over the lifetime of the queue, we have seen that in the case of the naive queue, we have used 14 operations. In the case of banker's queue, we only used 11 operations. So for this very simple example, very simple benchmark comparison of performance, the banker's queue performed better. But something that's quite interesting here when you look at queues, and in general when you look at data structures defined by functional programming languages, is it's quite common to look at what's called amortized cost. So we don't look at just the cost of one operation. Say, what's the cost of adding? What's the cost of removing? Because in the case of the banker's queue, the question, what's the case of adding, has a good answer. One operation. But if I ask you what's the cost of removing, then I don't have a good answer, because sometimes it's going to be a lot of operations, but sometimes, most of the time, is going to be only one operation. So in order to do that, when you want to assess the performance, and that's something that's a good idea to do when you want to assess the behavior of complex programs, you don't just do one operation and you look like, was it efficient or not? No, you do a lot of operations, and then you look over the lifetime of that data structure, how many operations were made, if you want to compare them. Because, so as I said, for the naive queue, the add is in linear size, and the constant is in, and the remove is in constant size, 1. Whereas for banker's queue, the add is a constant, always 1, but the remove is sometimes 1, sometimes is a big number. But if you amortize it over the lifetime of the usage of the queue, you're going to see that actually the cost is also a constant, but it's going to be a constant that's greater than 1, because that cost of reversing the front queue into the back queue is not very large, is linear. It's proportional to the, linear means proportional to the size of the queue, but it happens relatively rarely, this need to flip the queues. And now this, to actually, there's complicated mathematical techniques where you can actually prove that. And you can say that, yes, that is the average cost. But that is really quite hard to do. But what we can do is a little bit more sophisticated benchmarking. So let's do a benchmark like we did in the case of a tree. So first of all, it's a good idea to try to have a self-contained implementation where we don't make library calls. Because if we make library calls, we don't see how many steps are actually executed in the library call. And that can be tricky, because you say, oh, I'm just making a library call. And it's just the cost is 1. But actually some library calls have very high cost. You don't see the cost. It's like a black box to you. So I'm re-implementing the append operator. because that's where the majority of the effort, the majority of the computational effort is going to be spent. Yeah, so it's grayed out because it's just a re-implementation of a standard library, and also enqueuing and dequeuing and empty testing. I replace the tail call from the library with an explicit implementation of it. Where what's the tail? Well, I pattern match the list against head and tail, and I drop the head. And again, this is not a very nice implementation because it's gonna give me a compiler warning and a nasty runtime error if I try to dequeue from the empty list. For the banker's queue, this is the implementation, the one that I have showed before. And now I also have to implement, in order that we're self-contained, the reverse of a function, what it means to reverse of a function. And of course, I'm giving it the more efficient tail recursive implementation of reversing. Because if you give the naive implementation of reverse, which is not tail recursive, then the performance is going to be a disaster. And now we have to write a benchmark. A benchmark means the same program that has to do a lot of enqueuing and dequeuing, and we're going to run it twice, with the first implementation and with the second implementation. So let's take this program. It's a function called benchmark, well, bmark_q, and it's going to have a counter that's going to count down. When I call it first, I'm going to call it with the value 10,000, and it's going to count down to 0. And when we reach 0, it stops. And at every end, so this is like this is a while loop basically, or a for loop from n equals 0 to 10,000. So at every step, I'm going to create a random value from 0 to 4, so 0, 1, 2, 3, 4. So there's going to be 5 random values. And because I want my queue to grow, I want to deal with a big queue, I'm going to make the likelihood of enqueuing bigger than the likelihood of dequeuing. Because if I make the likelihood of enqueuing and dequeuing equal, then the queue is going to be always very, very short. And then you're not going to really see the difference in performance. But if we make enqueuing much likelier than dequeuing, then the queues are going to grow very big. Now this is a design choice. Yeah, this is by making this choice, I'm testing a particular kind of behavior. It's not a universal or a canonical choice. So if you fiddle with that, you might get different results. So whenever you do benchmarking, and that's a complaint of people because benchmarking is a big field. That's how a lot of the programs are tested for efficiency via benchmarking. There is a lot of subjectivity going on into benchmarking. So when I write the benchmark like this, it may not fit a particular usage pattern that you have in mind. This is a benchmark where the queuing is growing. The queues are growing. Yes?
What does the yellow text say?
So you cannot see it says no empty queue. Not empty queue. So we're dequeuing only if yes. No, we're stopping. Yeah, we're stopping if the queue becomes empty. So yeah. So this is how the profiling numbers look for the naive queue and for the banker's queue. So for the naive queue, you can see that there were, in blue, you can see there were 7,900 calls to enqueuing and about 2,000 calls to dequeuing, and that was matched by the calls to empty because we always test that we're not dequeuing from the empty list. If it's empty, then we stop. So you can see that they add up to they add up to 10,000, and they have kind of the ratio that 1 to 4 ratio that comes out of the likelihood that we chose. And the number of enqueuing, you can see that it matches the number of the number of empty list tests in the append, because whenever you enqueue, you always have to go all the way down to the empty list, and that's when you append. And now in red, you can see the big number where most of the computational effort is spent. Most of the computational effort is spent in the recursive call of append. So most of the effort is shifting the front of the queue past all the elements until it gets to the back of the queue. So in dealing with 10,000 enqueuings, we made it to we needed 23 million append operations, which is really a lot. Now, in the case of the bankers' queues, the numbers of NQs and DQs is the same, because the random number generated is seeded in the same way. So the same random sequence of NQing and DQing, it's used for both programs. You can see there in orange, 6 is how many times we needed to flip the front queue to the back queue. So we did 10,000 NQings and DQing, and we needed to flip the list only 6 times. So that's, in this usage scenario, it was relatively rare. And in total, in red there, most of the computational effort was spent in doing this reverse operation. But now, instead of millions, there were only 2,000 or so reverse operations that we needed to do. So even though it doesn't seem intuitively, at least to me, it doesn't seem like just by reorganizing your queues like that, you're going to get a big gain in efficiency. You actually get a massive gain in efficiency. But there is another way of implementing queues which is even better, and these are the imperative queues. And the idea is that with every queue, you store somehow the address of the next element. So now whether we add in constant time. Whenever we add in constant time, and whenever we remove in constant time. So this is by implementing the queue as pairs of data, where you put the element, and a pointer that keeps the address. It's called a pointer, but it's really the memory address of the element that's in front of it. And in this case, you can implement both enqueuing and dequeuing in constant time, and you don't have any implicit or explicit overheads. But this is the kind of stuff that you are going to see in a lot more detail next term. Because in this term, we looked at these data structures that can be defined in functional languages. But next term, you're going to look how most data structures can also be implemented in functional in imperative programming language, using this idea of a pointer or an address, where every element somehow has a link by remembering where its child or its parent or whatever is in the data structure. Now, I said these are not inductive data structures, so how do we reason about them? And it turns out we cannot really reason about it directly, because we don't have an inductive principle for queues, and we don't have a recursion principle for queues. So one way we can do it is we can take the naive representation of the list, the one that is just a queue, where you add at one end, and then you use append to add at the end, and then you use head-tail pattern matching to remove from the other end. Because the difference between the naive representation and an efficient representation is just one of efficiency. It's not one of input-output behavior. So it doesn't matter what your implementation is. If you start with an empty queue and then you NQ, then you DQ, you end up again with an empty queue. So this property in some efficient implementations might be difficult to prove, but if you reason in general about the naive implementation, which is the simplest, and you just show one big result, that the efficient representation is in some sense equivalent to the naive implementation, then that gives you a way to prove properties about queues. We're not going to do that because in principle you should know how to do it, but there's all sorts of practicalities that might get in the way. So I hope you don't mind if I stop 2 minutes early, and see you next for the last meeting. See you on Thursday.